Hi, hello guys. So today we're going to use the concept of proof by contradiction. Okay, so it's an unusual way of proving things, but it'll make sense. The one that classically comes up, the one that's only ever come up, but I will do a couple of other examples for you just in case. The one that ever comes up is to prove that the square root of 2, or it could be the square root of 3, is irrational. Okay, so if you remember the rational numbers, the Q numbers, they're numbers that can be written in the form of A over B, where A and B are elements of the integers, and B is not equal to 0, type of thing. So that's what a rational numbers is, and because root 2 is irrational, there's no way of writing root 2 as a rational fraction. You just won't get it. It's impossible. So there's lots of ways of proving this. You can prove this geometrically, but I'm going to prove it using proof by contradiction. And the idea of a proof of contradiction is we make a statement, a while statement about the root of 2, okay? And we prove that while statement can't be true by trying to prove it's true. At some point in our proof, we'll come across and contradict what we've just said at the start. Okay, so here's my assumption. Square root of 2 is rational. Okay, therefore, it can be written as A over B, where B is not equal to 0 and A and B are co-prime. Now, let me explain what co-prime is. There's other ways of writing it. You can write it just as, A and B are elements of the integers, and that A and B have no common factor, apart from 1. So in other words, you can't cancel them down. That's a long-winded way of saying they're co-prime. Co-prime means that the only factor both of them have in common is 1. It's a fancy way of saying that. For example, I could have 2 over 9. Okay, 2 is prime, 9 is not prime. However, 2 and 9 only have a common factor, which is 1. Okay, another example could be, let me see, 4 and 9. Okay, 4 is in prime, 9 is in prime, but neither 4 or 9 have a common factor greater than 1. Okay, so that's what we mean by, co-prime. Okay, but you can't, if you don't want to remember that, just say A and B are elements of Z, the integers, and they have no common factor. Okay, so that'll do the same job. So let's declare this then. Well, if that's true, then surely I can write A over B is equal to the square root of 2. Okay, so I see a square root. How do I get rid of a square root? Well, I square both sides. Therefore, I can square both sides. So that means A squared over B squared is equal to 2. Nothing too crazy there. See a fraction? Let's get rid of the fraction. Okay, let's go with A squared is equal to 2B squared. Again, nothing controversial there. I haven't contradicted myself. There's nothing wrong there, but I am noticing something. Okay, A squared is even. Why? Well, because A squared is equal to twice B squared. And when you have twice any number, that number is even. So twice 7 is 14. 14 is even. Twice 51 is 102. 102 is even. So whatever A squared is, we're saying it's equal to 2 times another number squared. I don't care what that other number is, but if it's 2 times it, that means I could divide that number by 2 and still have no remainder. So that is even. So A squared must be even. Interesting. Okay, but think about this. If A squared is even, well then surely A must be even. Because any squared number that's even, 16, 100, 64, 144, they're all squared numbers and they're all even. So if the squared number is even, then the root of that square number, if it is a whole number, if it's an integer, which we said it is at the start, it's even. See where we're going with this? Okay, so you can see where this is building to. Okay, We have a little bit of a contradiction starting to form in our heads. But listen, we can write A as, 2 times another number because it's even. So every even number can be written as 2 times another number. Okay, because that's why it's even. 2 can be written as 2 times 1. 4 can be written as 2 times 2. 16 can be written as 2 times 8. So you can always write it as another number. Okay? So if A can be 2n, then A squared can be 4n squared. Okay? But we already know that A squared is equal to 2b squared. So, using our logic, 4n squared is equal to 2b squared. That means b squared is equal to 2n squared. That means, and we can see the same thing that's going to happen here, that b is even. Why? Because any squared number that you said is even, that means the root of that number is also even. And there we have our contradiction. Because A and B are even. And we said they're either co-prime or they have no factor, but if both of those were even, I could divide both of them by 2. And there's your contradiction. So the square root of 2 cannot be rational. Because it cannot be written as A to the form B, A over B, where A and B are in their lowest form and you can't divide them anymore. So there is your proof by contradiction. Okay? You can do this a number of different ways, using a number of different, but basically your strategy is to prove that you only need to prove that one of them is even. But I proved both of them are even. You only had to prove, you could prove one of them is even and then just flip the story around and reverse the process, and you can prove the other one could be even as well. So if both of them are even, both of them are even, you've got the game's up. It's a contradiction. Okay, so that's your basic contradiction proof, and that's the one that's come up multiple times. Okay, so I'll show you another one. It's that type of guy. Okay, so there's another one. Okay, so I'm going to prove that if A is rational and B is irrational, then A plus B is irrational. So, in other words, let's say I have 2 and I have the root of 2. And if I add 2 plus the root of 2, the answer is an irrational number. I can't, write 2 plus the root of 2 as a fraction. Same idea as the other one. Okay, so how am I going to prove this? Well, I'm going to use the same strategy. So I'm going to use the same idea. So I'm going to say to myself, I'm going to use a proof by contradiction. I'm going to say that, I'm going to assume A plus B is a rational number. And then I'm going to try and prove that I've caught myself out in a line. Okay? So, if this thing is a rational number, okay, then A plus B can be written as, P over Q. The usual thing, P and Q, elements of the integers, and, Q not equal to 0. Okay? Same setup. Okay? Whatever this number is, I can write as a fraction, and both those terms cannot be, they're integers, they're either positive, negative whole numbers, and the bottom number cannot be 0, otherwise it doesn't work. Okay? So, let's just take A. We're saying that, A is a rational number. Okay? So, let's just take A. If A is rational, then A can be written as, x over y. Okay, same thing, x and y elements, the integers, and y not equal to 0. So I can write that bit. Okay, so if that's true, then if a plus b is equal to p over q and a is equal to x over y, well then surely x over y plus b must be equal to p over q. So all I'm doing is just taking my original statement and replacing what I've declared x or a to be by x over y, leave b because that's your supposed rational bit, but I'm saying when I add those two, I'll get a rational answer. Okay, right, so let's have a look at this. That's b, isn't it? That's meant to be our irrational number. Okay, so that b is going to be equal to our answer minus a. Okay, let's get a common denominator here. Qy, and q into qy goes py times, minus y into qy goes xq times. Okay, but that's b. And what do you notice about b? Every one of those letters is rational. It's rational. But we said that a was a rational number and b was an irrational number. And we didn't change b the whole way down. This is a contradiction. Because somehow b has become rational. Why? Because everything there is a rational number. It's rational on the top, it's rational on the bottom, and rational over rational is rational. But we need b to be irrational, and it ain't. So there it is. So it's a contradiction. So a plus b must be irrational. QED. Okay.